Hi everybody. Today we will solve a rolling motion problem which will include rolling with slipping and rolling without slipping. Two different cases. So we already discussed rolling motion, and this would be a nice example to see the difference between these two kinds of rolling motions. Okay, initially what's happening is we have an object, a rigid object, whose center of mass is here right in the middle. So it may be a sphere, a cylinder, a hoop, a ring, we don't know what it is, but it has a circular cross-sectional area with radius r. Initially it is just rotating right above the ground. Okay, so when t is equal to 0, we just release it. So we drop it. And then it starts to slip to the right. Okay? So a distance of d. And at some time t, okay, it starts to roll without slipping. So it will have a center of mass velocity pointing to the right, and there will be an omega angular velocity with respect to the center of mass of the object. Okay, in part A, we would like to find this omega in terms of omega naught I, m, and r. So I is the moment of inertia of this object with respect to the center of mass. Okay, so we can start solving the problem, but before doing this, I'll just draw it here. So while it's moving to the right, so let's show all the forces acting on the object. So there is a normal force due to the ground, right? And there is going to be, of course, force of gravity, mg, pointing down. Okay. And what else? So there will be friction, right? So what kind of friction? Since it's going to be rolling motion with slipping here, so let me put it this way, rolling with slipping. So force of kinetic friction is going to be to the right. Why? Because while the object is moving like that, so it's going to push the floor backwards, and the floor is going to push it forward. Okay? And this is the only force pointing to the right, so that it can move to the right. So this is good. So we have then a torque equation. We can write down a torque equation. So let's look at the rotation part first. So Fk is the only force which produces torque here with respect to the center of mass. Torque due to mg and torque due to the normal force, they are both 0. However, this is now my positive direction, right? I'm going to choose the direction of omega naught, like clockwise and omega. This is going to be my positive direction. So the linear acceleration is also positive to the right. So clockwise direction is positive for rotation. Then the torque is actually equal to minus F kinetic times R. Okay, then this should be equal to I times alpha. Torque is equal to I times alpha. So alpha is equal to simply minus FKR over I. And that's it. So let's look at the translation part. So there will be force to the right, F kinetic. So F kinetic is going to be equal to mass times acceleration, right? So the acceleration is simply equal to F kinetic divided by the mass. And that's it. So in between these two states, there is rolling with slipping. So this alpha and this A are not related. Okay? So we cannot write A is equal to R times alpha. No, this is not right. Because this is the condition for rolling without slipping, right? So these two are not related. So for each of these, I can write down the kinematics equations, okay? And this is what I'm going to do next. Earlier, what I found was alpha is equal to minus FKR over I, and a is equal to fk over m. It's the linear acceleration, this is the angular acceleration. So since they are both constants, I can simply use the kinematics equations. For this one, I can write omega is equal to omega naught. So the final omega is going to be equal to omega naught minus fkr over I times t. Okay, so this is how I can write omega as a function of time. And for a, I can write down v is equal to v naught plus fk over m times t. However, initial velocity, center of mass velocity is 0. So v is simply equal to that. So we have two equations like that. So since there is no any time in the problem, I want to get rid of, I can eliminate the time here, right? So using this equation, I can write down time is equal to, or I can write it here, time is equal to mv over fk. Okay. Okay. So if I put this time here, what I get is omega is equal to omega naught minus fkr over I times time, which is going to be mv over f kinetic. So what's nice here is f kinetic cancels, and omega is going to be equal to omega naught. Okay, so watch out here. When we reach this center of mass speed, okay, this and that are going to be related, because after this point on, v and omega are related. Okay, so we can write v is equal to r times omega. This is not true in between these two states, but after this point, okay, this is the point where it starts to roll without slipping. So then v, the final v, is going to be equal to r times omega. So here, wherever I see v, I can write r times omega. So this is nice. So this is minus r over I. So let me put it in a nicer way. So omega is equal to omega naught minus r over I m times omega times r. So this is r square. It's going to be omega. Okay. I can actually write it in a little bit nicer way. Omega is equal to omega naught minus mr square over I times omega. So I can put this term on this side and I can use the omega parentheses. So in the end, what I get is, for part A, this is my solution for part A, omega is going to be equal to omega naught over 1 plus mr square over I. So in part B, I want to find the change in the total mechanical energy of the system. So in the final state, I have rotation and translation together. So I'll have 1/2 mv square plus 1/2 I omega square minus, initially I only have rotation, so it's going to be 1/2 I omega naught square. Well, this is nothing but the change in the total mechanical energy of the system. There is no any change in the potential, potential energy. So now I can put it in a little bit nicer form because I know how omega is related to omega naught. So I can write everything in terms of omega naught maybe. So let's see how it works. So 1/2 m So by the way, V is going to be equal to R times omega as before. So this is going to be mR square, then omega square, plus 1/2 I omega square. So I can just use the common parentheses here. So instead of omega square, I can write omega naught square over 1 plus mR square over I square minus 1/2 I omega naught square. Good. So here I can simplify it a little bit more. So delta E is going to be equal to, so 1/2 mR square plus I, and I'll have mR square plus I if I equate the denominators here. Okay. I omega naught square divided by, I'll have mR square plus I parenthesis square divided by I square, so it's going to be I square here. Okay, and then minus 1/2 I omega naught square. Okay, so you can cancel one of these terms here. So then what we have is, I have 1/2 I omega naught square, I have 1/2 I omega naught square. So delta E is going to be equal to 1/2 I omega naught square parentheses. Okay, so I'll have I over I plus mR square minus 1. So okay, so what is that? So if I equate the denominators here, so it's going to give me minus I minus mR square, right? So this I cancels that I, and I get a minus sign here. So if I want to write it here, the answer to part B would be equal to minus, so delta E is equal to minus 1/2 I omega naught square parentheses mR square over I plus mR square. And this is going to be the change in the total mechanical energy of the system. And this minus sign here signifies that the energy is reduced, right? So this friction force actually does negative work, okay? So we should keep that in mind. Okay, so in part C, we will try to show that the work done by this friction force is going to be just equal to that. Okay, change in the total mechanical energy of the system. And this is what we want to show in part C. Okay, let's move on. Earlier, we had found these kinematics equations from A and alpha, okay? And we get V as a function of time and omega, so these are V and omega. Omega is a function of time, okay? So in the last part, part C, we are going to be looking at the work done by friction, okay? This friction force is actually acting at the point of contact here. If we call this point C, it's acting at this point. So at any given instant of time, the velocity at point C is going to be equal to V, let's call it V prime, okay? So at any given time t, this object is moving to the right with some angular, with center of mass speed V prime, and let's say some angular speed omega prime. So V prime times minus R times omega prime. Why minus? Because omega prime R, the tangential velocity for pure rotation, is actually pointing to the left. We already discussed that in the discussion of rotation, the rolling motion. Okay, so what is the power due to this friction force, then it's going to be equal to F times V prime minus R omega prime. Okay, this is good. So now the work done by this friction force would simply be equal to F V prime minus F R omega prime. Let's call it dt prime. So t prime, the time changes from 0 to t. So we simply need to take this integral and show that this work done is really equal to change in the total mechanical energy of the system. Okay, since F is constant here, Fk, okay, we can take it out. So work done is simply equal to Fk integral V prime dt prime 0 to t minus Fkr, so these are all constants, integral omega prime dt prime from 0 to t. Okay, this is good. So this integral, the first integral is just v dt integral. So this will just give me the total displacement. Okay, so this is simply equal to d. Okay, but can I find what d is? Yes, I can simply find d using the acceleration here, Fk over m. So we had the third equation, as you may remember, v squared is equal to 2 times a Fk over m times d, right? So this term, the first term, is nothing but, so instead of Fk times d, I can write 1/2 mv squared. So this is nothing but 1/2 mv squared minus Fkr times this integral. Okay, instead of omega prime, now I can write omega naught minus Fkr torque divided by I times t prime, right? So for any time t, so omega naught minus Fkr over I t prime dt prime. Okay, this is good. So now what I can do is I can simply do the integral. Okay, so let me erase here. I think this part is clear as well. I'm gonna start from here. So now the work done by the friction force is equal to 1/2 mv squared minus. So Fkr omega naught times t, right? This is just constant. Then I'll have plus Fk square, so it's going to be Fk square R square over I. Okay, this is great. I t prime. So it's going to be t square over 2 when we do the integral, right? This is what we are going to get. Okay, so this is great. We're almost getting there, right? Now, I want to simplify this expression so that it's going to look like the change in the total mechanical energy of the system. So this is the work done by friction, as we know, and it's kind of time dependent here. So I want to eliminate this t in the equation. I already have 1/2 mv squared term here, so I want to get some like omega naught kind of stuff here, rotational stuff. So I think the best way to go with is this equation. So I'm gonna solve for t here first. So this is omega naught minus omega. Okay, so t is equal to omega naught minus omega times I over F kinetic times R. Okay, so wherever I see t, I'm going to put it. So the work done is equal to 1/2 mv squared minus FKR omega naught times time here, I omega naught minus omega, okay, FKR plus the last term here, so let me continue here, plus Fk square R square over I, so there's a 2 here, times T square, so we will have I square over Fk square R square, I square, and omega naught minus omega square. This is good. So let's see what we get. So omega, work done, okay, not omega, this is work done, is equal to 1/2 mv square. Okay, let's cancel those. So FKR, okay, I'll have minus I, okay, and I have omega naught here, so this will give me omega naught square plus I, right, minus I omega naught square plus I omega naught plus the other term here, so Fk square R square, and I can cancel one of the i's here. So it's going to give me 1/2 I. When I expand it, this gives me omega naught square minus 2 omega naught omega plus omega square. Okay, this is good. Can further simplify that. Okay, the work done is simply equal to 1/2 mv square. Well, I have minus I omega naught square here. I have plus 1/2 I omega naught square here. So this is going to be simply equal to minus 1/2 I omega naught square. So I'm done with, I got this term, I got this one, and I got that one. So let's look at the cross term here. So I have 2 divided by 2 is 1. So I have minus I omega naught omega. But I have plus I omega naught. So these two terms simply cancel each other out. End up with the last one. So it's going to be 1/2 I omega square. Okay, and I think we proved that, right? In the end, let me write what we get. Work done by the friction force is simply equal to 1/2 mv square plus 1/2 I omega square minus 1/2 I omega naught square. And this actually proves that the work done by friction is really equal to the change in the total mechanical energy of the system. Okay, so if we put the values, I mean this expression here, we got that one. We already solved it in part B. So I think this problem was so nice to see when we can use A is equal to R times alpha, when we cannot use it. So this was the difference between rolling motion with slipping and rolling motion without slipping. People usually get confused with it, but it is not that hard. As you see, if there is rolling motion with slipping, you simply write down the torque equation and F is equal to ma equation, and you treat them separately. And when the motion starts rolling without slipping kind, okay, you can always use V is equal to R times omega or A is equal to R times alpha. So we also show that. And in the end, the work done by friction, since this is a kinetic friction, there will be change in the total mechanical energy of the system, and the energy is reduced, of course. So what happens here is actually omega gets slower, so the rotation is slowed down, but the translation is kind of picking some speed, right? So it starts to move to the right, but its rotational speed decreases in the meantime. But overall, when we looked at the overall picture, the total mechanical energy is reduced. So here, First of all, it seemed like, so when there was friction like that, some people may think that this is gonna do positive work, right? But it's not the case, because there is still rotation here. This is applying a negative torque on the system, so it's reducing the rotational speed, and it's also reducing the rotational kinetic energy of the system. Okay, so we need to be really careful here. So kinetic friction here does negative work, and we also prove that. I think that's all for this problem. I'll try to solve more problems on rolling motion with slipping, so that we will all get used to the concept. I look forward to seeing you soon. Take care of yourselves, study well, stay safe, and be happy. See you later, guys. Bye.